So in section 6.5, we look at the log properties. Now, these are properties that we're going to need in order to be able to solve equations. They give us a way of manipulating logarithms in order to work with them further. So just a reminder of the basic definition of a logarithm, right, is that y is equal to log base a of x if and only if a raised to the 1 y power is equal to x. So we're going to use that definition in order to explain those first couple of log properties. So when you look at number 1 on the list, again, the numbering is just so we can communicate. It's got nothing to do with the world's logarithm properties or anything like that. So they're just so we can communicate with each other. And you do need to know these as soon as possible. So the more practice you get, the better off you are. So property 1 basically says that log base a of 1 is equal to 0. So this is saying the log of any base of 1 is equal to 0. So I'm going to ask a couple of questions. The first one being why? Well, if we use our definition of a logarithm and switch this to exponential form, this reads a to the 0 is equal to 1, which is true. We know that anything raised to 0 power is 1, which is why the log of any base of 1 is equal to 0. Property 2 says log base a of a is equal to 1. So same question, why is that true? So we'll switch forms. This would be a to the first power is equal to a, which is true. So again, it may not make sense in the logarithmic form yet, but when you switch it to exponential, it will make some sense. Property 3 simply says that if you have log base a of a raised to the power r power, then the answer is the exponent of r. So again, why? So we'll switch forms. So this base raised to this power, a to the r, is equal to the argument, a to the r, which is true. So you can see that. The next one is a power property, and it feeds off of this one. It says log base a of m to the r power is equal to r log base a of m. So this one's called the power rule, and we will use it a lot. So basically what we're going to do is the logarithm allows us to take that exponent on the inside and move it or bring it down. Kind of looks like a coefficient. It's not really, but I'm going to call it a coefficient because we need something to call it. We also have a property that says if I take a base of a and raise it to a log with a base a of m, then the answer is m, the argument. Property 6 is the one that lets us take a product and turn it into a sum. So if I have the log base a of a product, m times n, then that's going to be equal to log base a of m plus log base a of n. So we'll use this to expand logarithms from a product into the sum of two logarithms. We have log base a of m over n, that's quotient. And if we have the log of a quotient, we can separate it using a difference of those two logarithms. So log base a of m minus log base a of n. So if I have a quotient, I can rewrite it as a difference. If I have a difference of two logarithms, I can rewrite it as a quotient. Finally, I added on, because this one is one that people tend to freak out about. Log base a of 0 is equal to, is undefined, because how can I take a, raise it to a power, and end up at 0? I can't. We saw when we were dealing with the exponentials, it didn't matter what we were plugging in for those exponents, we never got down to that y-axis. So, okay, so those are our properties. We're going to use them. Example 1, we'll work the first couple of them, just getting some practice with the basic properties, we'll call them. So we want to use the properties of logarithms to find the exact value of each expression. We are not using a calculator. A lot of your calculators will do this kind of stuff, but you want to practice without that calculator, please. So in example 1, part A is asking us for the log base 2 of 2 to the negative 13 power. So when I look at that, I notice that the base and the 2 are the same number. So the 2 and the argument are the same number. So we're going to use this property number 3. So if the base and the argument have the same, then the answer is the exponent. So this is equal to a negative 13. There are a couple of ways you could think about that. Think about this in terms of, if we use our power rule, that would be a negative 13 log base 2 of 2, and log base 2 of 2 is 1. So the answer would be the negative 13. So you can see where it's coming from. B on that one says, what about the natural log of e to the square root of 2? So a gentle reminder that the natural log of e is the same thing as log base e of e to the square root of 2. So our answer is, again, the exponent, which is just root 2. So again, the base and the argument are the same. You're left with that exponent. Part C in that problem says, what about log base 8 of 16 minus log base 8 of 2? Well, we've got two separate logs. They're separated by a minus. So it's the difference of two logarithms. So we're going to use this property 7 to combine them into single logarithm. So this would be log base 8 of 16 divided by 2. Well, 16 divided by 2 is 8. So that's log base 8 of 8. Well, log base 8 of 8. Again, if the base and the argument are the same, you're left with a 1. And then finally, part D on that problem says, what if we have 3 log base 3 of 5? So this is one of the more obscure log property rules. You won't see it a lot in our class or pre-calc, but Calc 1, especially Calc 2 is where you see this one a lot. So 3 log base 3 of 5, that looks like this guy, property 5. I have a base and I have a base, and they're the same, so I'm left with the argument, which in this case is the 5. And again, remember that logarithms and exponents are inverse functions of each other. So this base of 3 and this log base 3 are undoing each other, and you're left with that 5. It's one way to think about it. It works. And then we're going to use log properties to do some evaluation when we don't know the base. I'll admit these are some of my favorite problems. So in example 2, it starts off by telling us that the log of some base A of 2 is equal to 0.3456. Goes on to tell me that the log of the same base A, but I don't know what A is, of 3 is equal to 0.5298. So they give me that information, and they're asking me to use the properties to find each of the following. So they want to know what the log base A of 6 is. So I look at that and say, well, I don't know, what are we supposed to do? Well, our goal is to rewrite the argument, the inside piece, in terms of the two numbers they gave us. Well, they gave me a 2 and a 3. Well, we know that log base A of 6 is really log base A of 2 times 3, because that's what 6 is. Well, the minute I write it as a product, I can then split it apart using our property. So that would be log base A of 2 plus log base A of 3. So I have the log of a product. I can write it as the sum of the two logarithms. So notice I've written the word log twice and put a plus between them. Now, once I have that, all I need to do is replace. So we're going to take out the entire log base A of 2 and replace it with its decimal, 0.3456. There's no longer a logarithm in that term. We're going to do the same thing with that second term. We're going to take log base A of 3 and replace it with its decimal equivalent, 5298. And at that point, all you have to do is simply add the two decimals together, and you'll end up with 0.875. So we've just evaluated the log base A of 6 from the information that they gave us without having to use our calculators. Part B is asking me for the log base A of 9. Well, log base A of 9, you can treat this a couple of ways. We're going to recognize that 9 is 3 squared. Our power rule says we can move this 2 out in front. So I'm going to bring the 2 out in front. So I have 2 log base A of 3. And now that I just have log base A of 3, I can do the replacement. So I'm going to take out all of that and replace it with its decimal. So 0.5298. And we have the 2 times that. And if you take 2 times that, you're going to get 1.0596. Wonderful. Part C, same example. We have log base A square root of 2, very similar to the previous problem. The first step we have to do is realize that that radical is a fractional exponent. So that would be 2 to the 1/2. And again, what we're remembering is that the nth root of A is equal to A to the 1 over n power. So the radical becomes a fractional exponent. Then we can move that out in front using our power rule. And we have 1/2 times the log base A of 2. Again, when you bring that exponent out in front, it is a product out in front. It's a multiplication. It's times. So this would be 1/2 times the equivalent of log base A of 2, which was 0.3456. So I'm basically cutting 0.3456 in half, and I'm going to get 0.1728. Part D says, what about log base A of 3 over 2? Well, that's a quotient, and we have a property that tells us if we have the quotient, we can rewrite it as the difference of those two logarithms. So end up with log base A of 3 minus log base A of 2. Now we'll do our replacement of 0.5298 for the log base A of 3. And log base A of 2, we're going to be 0.3456. We'll just subtract those two, and if we do that, we end up with 0.18. That's our answer. Beautiful. Then the last one, part E. Sorry, I ran out of room. We'll do it over here. Log base A of A is a trick question. That A is not part of the information they gave us, but we know that if the base and the argument are the same thing, the answer is A1. So. Okay, next we'll work on expanding and contracting.